Hi everyone, thanks for being here. So today we're going to talk about unexpected behaviors in C++. So I'm Antonio, and here with me it's Jaime. Just a couple of words about us. I recently had a career change. I started a PhD about efficiency and information retrieval, applied to information retrieval, while Jaime is a software engineer at Bloomberg in London. Those are our contacts. Feel free to contact us about this talk or anything else that relates to CPP. So why are we here today? Motivations for these talks come from the fact that C++ is a bit obscure to both beginners and professionals. Most of the time we do assumptions on code behaviors, and these assumptions sometimes translates to bugs in our code base. So we are going to present today some examples of typical and maybe even famous snippets of code that doesn't behave as most of the programmers would think it does. This is because then we will try to be more careful on this kind of situation where we have to maybe slow it down, take it easy, and analyze what is actually happening. So let's start with some definitions. Usually, well-formed C++ program, not like the behavior of a well-formed C++ programs can be classified in three main categories when it's not defined by the standard. And typically, it's implementation defined, or it can be unspecified or undefined. Undefined is probably undefined behavior is the most known, probably. The other two, implementation defined and unspecified, differs a bit among the two. Implementation defined, just to recap, it's when it's up to the implementer to give a behavior, to specify a behavior. And while unspecified is the same implementation can behave differently by changing, for example, in a compiler, like the compilation flags or similar things. So any of this can result in the end, and this is where we are affected, in unexpected behavior. So let's abbreviate unexpected behavior UXB just to get rid of the UB confusion. And let's define it basically as like an undefined behavior happens basically when a program doesn't behave as with the same behavior that the programmer initially intended to give to the program. So this actually then is causing some undesired results. In a Venn diagram, we can place unexpected behavior intersecting the three sets of categories that we already defined before. And it's the inner set of the diagram. So how many of you still see C arrays in C++ codes? Oh, OK. Perfect. I wasn't expecting this answer. Anyway, so everybody knows how to define an array, a C array, how to access a C array. You basically just use the square bracket operator for both read and writes. What happens if you swap the offset with the array? Does this compile? Yes. Do you also know why? OK. Random choice. Hands up if you want to explain why.
Well, it's defined as just a pointer a plus 5, and addition is commutative, so 5 plus a is the same as...
Exactly. That's exactly what happens. So for the commutative property of the addition, this is exactly the same for the two. But that's, for me, it's confusing. If I was a beginner, that would have confused me. Actually, it still confused me. Because what happens is, if 5 was just a variable, you see, for example, A and B as an array and a static variable, a const variable, then you just started messing up the two things. So when you, like, C++ introduced the concept to, like, evolved C somehow with the object-oriented programming concept. So now we have encapsulation in C++ with respect to C. So encapsulation is defined from a Wikipedia definition as basically something that is preventing unauthorized access. So we are trying to hide and mask the state and the methods of a class, of an object. So let's imagine that we have this snippet of code. We have an account, and it's a bank account. We have a status of the account, so which is the account balance. And we have two, the API of this account is basically you can deposit some money, and you can print the balance of the account, of your account. So far, I guess so good. Yeah, you put your money in your account, you get your balance. Then you want to extend it, because you got a job, and yeah, you have an employee account. So this employee account has a private method, which is accessed by a third party. It's private because you cannot pay your salary, obviously. But what this method does is just increasing your account balance by a fixed amount of money every month, right? So the way you exercise these classes is basically you can instantiate an account, make a deposit, get your balance, and hopefully this is what you deposited before, if you can trust your bank. Then you instantiate an employee account, and you try to pay your salary. Would this work? It doesn't, because it doesn't compile. So what happens if the base class at some point starts having a pay salary method, which is, on the other end, public? Is this code going to compile? Yes? No? Yes. Let's see who says yes. So this code compile. You sure? Say it again? Yeah, right. But the other one is public.
Not the method, the variable. The method variable is private.
Yes, the variable is private.
The second class might not compile. The second class will not compile.
Yeah, the second class is not compiling. Okay, so it's a protected variable, right? It doesn't change, but except for that. The call. Yeah.
For this interface, the method is private, so you need to cast to base.
Right. This is exactly what we want to do. If we cast it to a base account, a pointer to a base account, then we can call the pay salary. We are actually executing the private method. And we are getting our balance increased. And I've saw this code to test basically private methods, to create unit tests of private methods. And I think, yeah, I mean, that's good. You get rich if you put it in a while true, but that's not what we want. So let's move to something else, something different. Long arrow operator. How many of you have heard about long arrow operator? OK, fair enough. So what is this code doing? Anyone? Suggestions? Bringing us to 0. So long arrow operator is like what? A limit? Bringing x to 0 is the correct answer, but there is no long arrow operator. It's not an operator. It's equivalent just to a comparison and a pre-decrement. So what if we make it longer? And I mean, so we saw that the long arrow operator is not a single operator. It's a composition of multiple operators. And in this case, it's just a normal arrow operator plus a postfix decrement operator. Yeah. So in this case, it's two postfix decrement operator plus a single arrow operator. Can we overload them? Yes. Yeah, we can. We can start thinking about a wrap class, which has two different overloads. One will return a pointer to the inner object, and the other one will just return a reference to the object. How do we use it? We can use it, basically, it can be useful to different nested pointer-like structures, like, I don't know, unique pointer, shared pointer, optionals. And it can, the bad side of the thing is that it can become potentially limitless. Do we want it? I don't know. No, we don't. We can use if context in this case, from C++ 17, obviously, and we can keep on wrapping with this function until we get to the pure value. So the idea is, if wrap v is actually a wrap, keep on wrapping. Otherwise, get me the reference. And the way you define the two type traits is basically, if it is a specialization of a wrap, then it's true, otherwise it's false. So I saw something similar in a previous talk during this meeting C++ conference. So let's imagine I want to say everyone, hi. I want to greet everyone. And I still don't know how to say it, so I just accept as a parameter a string. Then I say it in Italian, because I meet some Italian friends, and I just say, hey, ciao mondo, hello world, in Italian. And this works and prints hello world, I hope. But what happens if at some point I see, oh, there are many German speakers and many English speakers, obviously. So I want to switch between the two with an if condition. What is going to happen here? Hands up, who knows? Perfect. What happened?
The string is not a std string, but pointer to a string, and so it defaults to a boolean.
Great, exactly. That's not a string, it's a constructor pointer, which gets translated to a boolean. But which one of the two get printed? The true one. Why? Why the true one? It's not a null pointer, that's it. Yeah. So it's not a null pointer, so we print the German one, even if we still pass a constructor pointer. And that's, as I said, it's because like the conversion precedence is happening for a standard conversion first, and then for a user-defined conversion. So std string is a user-defined conversion, and then this is another example. So variant, we saw this during the debugger talk, and yeah, this is evaluated as a bool again. The way you prevent this is with C++ 14 string literals. You just append an s and use the namespace string literals. So overload resolution. I guess many of you are using the algorithm adder. And yeah, so let's say that we want to find if a vector or any other container contains a value for a value that is 1. So we have two overloads, one for is 1 for an int and one for a double. And the double obviously compares with the double. So we use find if with this vector, and what is going to happen? It won't compile. And we think why? There is an overload for that function. But unfortunately, the signature of the findIf function tries to infer the type for the predicate, but the type for the predicate doesn't depend on the type of the container in this case. So it's impossible for the compiler to resolve the predicate overload. Solution is wrapping the call into a wrapper using a call operator. So in this case, the wrapper is able to deduct the type inside the container, and then the right overload is called. Simpler version, using with lambdas. You can put everything, getting the same output, just using a simple lambda and an auto. So now Jaime is going to carry on with overload resolution with some other examples. So let's see.
Well, thank you, Antonio. Well, first of all, excuse me for my voice. I'm just coming off from a cold, and I clearly haven't recovered. But, well, I hope you're doing good so far. So here I'm going to continue with an example on overload resolution. So I think this is a very famous one that you may know. Let's say that I have a class that is a string converter and just have a function that takes in an integer and possibly returns a string representation. And then I want to extend this class, and I want to add another function that, let's say, takes in a double and returns its implementation, its representation, and the implementation will be different. So that's why I want to have different functions here. So let's exercise both of these. Let's have an instance of my child class, and let's take a pointer to the base class and call the convert function on both of them with an integer. So, well, who knows what happens here? So we would expect here to call the right overload. So in the first one, in the first one and the second one, to call the double one. But actually, in the second one, the parents class function is hidden. So it's calling the double, actually, because the overload resolution stops at that scope, which is the derived class in that case. So, well, fortunately, this has a simple solution. We should be explicit about the overloads that we want to include in our child class, and we can just import it with the using keyword, and in that case, we will just use the right overload in that case. Now I want to move to a tidbit that is also quite simple. It reminds me to the arrays one, and is weird behavior that I hadn't seen about the ternary operator. We're used to using it in the right-hand side of an expression for conditional assignment. But in here we see it on the left-hand side of the expression. So here we see that if a equals 0, we have a, or else we have b, or in the other case, we have a or c. And we assign that to 1 or 2. So, who thinks this is correct? So, well, half true. The first one is correct, but the second one isn't. And basically, the C++ standard says that for a ternary operator to be an L value, both of those need to have the same type, and A and C are different types. And this doesn't work in C. It's a C++ extension. So now I'm going to move into a different realm, the realm of optimizations and how we can alter the behavior of our code. Sometimes you can remove unused code. You can change the default values of variables, such as serial initialization or not, integers. So we will explore some of these examples. So here we have an example where we have a function that checks if this pointer is null. We do some stuff, and then we exercise it by having a null pointer and just checking if my resource is null. Well, in normal situations, we have a pointer to reference there, so you would expect the program to crash because the referencing null pointer is unexpected behavior. But actually, if we enable optimizations, we can see that the output may be false. So for a null pointer, we may get that the isNull function returns false. And this is because of two things. Well, one thing, the compiler may think that because the pointer is being dereferenced, it may not be null, so it may just skip the first part of the if branch, and it just returns false, and then it may remove the unused variable. So it will just simplify that function to returns false. Even though this didn't help us, sometimes it can help us. So as we know, signed integer overflow is undefined behavior, and we can't expect it to behave as we want when we add something to int max. But here we have a function that takes in an integer and just returns whether that integer is greater, whether the integer plus 1 is greater than itself. And we just exercise it here. So here we see that actually the compiler, this is a really simple condition, and it can optimize it to true. So in this case, the compiler helped us. It avoided this undefined behavior of signed integer overflow. Now, we always say that undefined behavior can do anything. It can set your house on fire. But normally, we always have some expectations around it. But in this case, it can be very dangerous, and actually, it can remove our files. So here we have a static function pointer, which is global and is not initialized. And here we have my evil function that removes my files, and an initialize function that initializes this static function pointer to that evil function, and then we call it. But in our main function, we're not initializing it anywhere, and we're just calling it. We're just invoking this uninitialized function pointer. But actually, the compiler can just optimize this to calling the function pointer. Well, it can do this because calling a not initialized function pointer is undefined behavior. So this example may seem contrived, but actually a more complex version of this was found in the Linux kernel. So we have to be careful about how optimizations can introduce unexpected problems. So as we know, it can optimize away reads of variables. So if the compiler determines that between 2 consecutive reads that variable's value does not change, it can optimize away that data read. So we can use volatile to prevent this. And it may also not zero initialize integers depending on the optimization levels. Of course, many of these can be found with compiler warnings or any standard static analyzer.
Can you God bolt it?
Huh?
Can you God bolt it? Can you run it?
Yeah, I can. Let's run it. Yeah, so here we see with Clang, with optimizations, we see that this call function just has the contents of my eval function. So it's just calling that system or MRF, even if we never call the initialize function, which is just empty here. So let's go back. So now with C++17 we get guaranteed copulation, and as we know, this has been in compilers for quite some time now in the form of return value optimization. So what we would expect from variables being copied or assigned is not always what happens. So here we have a simple example of a very noisy class that has print statements for the default copy and move constructors and the assignment and move operators. So here we have an example when we have some functions that generate this instance of A in very different ways. So we're returning an unnamed temporary, or we're also returning a named temporary. So of course here, any decent compiler will apply copulation or RVO, and actually with C++17, in these cases, it has to. So we just see that we call the default constructor 3 times. We just call it for all 3 of those functions, and the copy into A, B, and C is also elided. So that's, I think most people can expect this to happen, but actually we can try to trick the compiler a bit more. We can put in a condition here. We just have an integer, and we do something different whether that integer is negative or non-negative. We return this default constructed temporary value, or we just return a new unnamed temporary. And then we exercise it with -1 and 1. So actually, in the first case, the compiler could not optimize the move, could not default construct that object directly into the return value. And this is because at compile time, it cannot know whether that condition will be true or false. So it still has to default construct it and then move it explicitly. Then in the second case, of course, you can just default construct the first temporary, which will not be used, and then just default construct the second temporary, which will construct it directly into the return type. So, well, as we've seen, unexpected behavior can be caused by compiler optimizations. Sometimes if we have even undefined behavior, it can remove some variables and really alter the observable behavior of our code. So we need to make sure that, for example, in cases like we've seen with copulation, we don't have side effects that we would expect our code to go through, and that we depend on, because the compiler is now allowed to just strip that away. Also, in some cases, we may find obscure standard specifications that we may not know about. So actually, those ones cannot always be found by the compiler, so we need to make sure that our code tests for that. So of course, how do we prevent this? This is just a given. We need to enable all compiler warnings and address them, and use static analysis in our continuous integration process, and really make sure that we're applying the guidelines that like the C++ core guidelines that help us reason about our code and get the results that we expect. But of course, like I said, sometimes it's not enough. Sometimes these unexpected behaviors are not caused by optimizations or UB. Sometimes, of course, we cannot rely on this. So these cases only can be detected through testing of our code, through making sure that the contracts of our functions are well defined, and we really test the conditions, the pre and post conditions of our functions. So even if we as C++ programmers, we like to rely on the compiler to detect many of these things at compile time, sometimes it's not enough. So we need thorough testing for that. So, well, this has been our talk. This is where you can find our slides on that link or that QR code. And now we're available for questions. Thank you very much for attending. Yes.
Any questions?
So somewhere you showed an example where you wanted to call find if or something,
Yeah.
and you put a wrapper around it. Why not just specialize the function call, the template?
So, are you talking about this example?
The find if one.
Yes.
Yeah. So say is one and then curly like angle brackets int, for example.
But then how do you pass it to find if? You have to specify the type, right?
No. I think your question is that you can just have a templated function is1 and just do whatever you want, and just in that, here you can just put square brackets and it will just work. Well, of course, but sometimes you may have overloads that do different things. So even if this example is a bit contrived, we wanted to show that actually this can happen. So
Yeah. Thanks.
Like a comparison with a bool instead of
yeah.
One function comes from a library and the other function is
Ex-
done by you.
Exactly. So sometimes you may not know that the library may have one of these functions, and you may run into this.
I would even add that the whole purpose of overloading is basically to give different functions that semantically do the same thing, the same name. So as soon as you start to annotate which function exactly you want to call, this defeats entirely the purpose of overloading. So the version that uses a lambda or a generic wrapper is, in my opinion, strictly better than specifying here which one you want, because if you're going to program like this, then you could as well go back to C and make one function that converts integers and one that converts floats. So I mean, that's exactly what we have overloading for in C++, that you don't have to do these kind of things. So I would consider explicitly forcing the type of the is1 method here bad practice, in my opinion. So.
Should we extend the language to automatically make a lambda?
Let's wait for the microphone.
I tried to shout, yeah. Yeah, in this case, maybe the language would automatically put a lambda around is1 for us, so we don't have to think about this.
Well, do you mean that the language itself will put a lambda?
Yeah, for me, the lambda solution is kind of obvious, and there's only one way to write it correctly, so the language should just do it for us.
Yeah, well, but the language is not doing this. We just have this declaration for the findIf function. We just have this argument deduction for the predicate, and it can't really know anything else about the overload.
Yeah, well, but yeah, you often get an error that you can't pass an overload set in this position or something.
Yeah.
So the language should just say, well, I'm going to turn an overload set into a lambda around the overload set, and fix things.
Yeah, but I guess the compiler doesn't want to assume what you want to do and wants you to be explicit about the one that you're using. So in that case, that's the solution with a templated function would be closer to that. The compiler would just use the one that you want.
I'm not sure whether you said it, but why not just to cast it to pointer function type? I mean the third argument.
You mean, yeah, cast it there.
Yeah, to function pointer type. Oh, I don't know how you say that.
Yeah, I see your question. I'm not sure if that
yeah, it
work.
will work, definitely. This is what I do in these cases, but...
Yeah, no, I guess it will work.
So the idea is to cast it to the function pointer.
You can just write static cast to bool pointer and int, and yes,
yeah,
it's going to work.
We can discuss about it and let's see if it works. Yeah.
Oh, yeah.
The whole point of it is that you can change the type that vector is holding without having to change the rest of the code.
I can't hear you. I can't hear you.
Yeah, I mean, yeah.
I can't really...
No, I didn't.
Thank you.
No, I was just replying to what he was saying. I think the whole point of writing a wrapper function is so that you can change the type that the vector is holding without having to change the rest of the code. And if you cast it like you say, you cannot do that. Yeah.
But in this case, you know that the type of your value type of your... In this case, you know that your value type in your vector is int, so it's like, yeah, obvious that you want to use this overload, specific overload.
Yeah, but it's less general, right? Less generic, and yeah, you have to specify the type.
Generic range, maybe not vector, maybe vector and different values. Yeah, it might make sense to use wrapper immediately. It's kind of interesting solution.
I can't really hear you.
Wow.
Sorry.
Thank you.
Any other questions?
No.
Okay, thank you guys.